Welcome to another series of Statics of Rigid Bodies. Today we will be discussing about the application of coplanar forces, wherein we will discuss the free body diagram. The free body diagram of a structure is necessary in further analyzing its support reactions and the effects of its external forces. So our learning objective is to analyze line loads and their resultant. The second one is to define types and behavior of supports. The third one is to make a free body diagram of structure. And finally, to analyze the free body diagram of structure that we have made. So let us first describe pressure. Pressure is distributed loads that are directed normal to the surface on which they act. So pressure is different from force. So if you apply a certain force on an object using your hand, the force is distributed over the contact between the object and your hand, and that is the pressure. Now, if you have the same force applied to a smaller area, the pressure is larger compared to those or compared to the situation wherein you applied the force over a larger area. So if a force is bigger, the pressure is also bigger. So it is directly proportional. And likewise, P is inversely proportional to A. That means if the area is increased, the force is decreased. So a good example of how we appreciate the difference of force and pressure is when you try to press a certain part of your body, for example, your hand. So using the right finger of your hand and your left palm, as you can see, if you try to exert the same amount of force using your finger to your palm, you can feel that if you increase the force, it would somehow hurt a little bit. But if you try to use your fist to your palm, definitely it would have a greater area. It would not hurt, unlike when you have when you use the finger. So it is because the tip of your finger is or has a smaller area compared with your fist. That's why if you apply the force on the tip of your finger, it might somehow hurt your palm. But if you apply the same value of force using your fist, it would not hurt as much as those when you use your finger. So let's discuss surface load. So distribution of the load is specified by the function Pxy, or called the load intensity. As you can see in the diagram, the load intensity is shown by the height of the arrows or in the region V. And the unit for the pressure, since this is force acting over area, in metric we use Newton per square meter, and in US customary units we use pounds per square feet. Now, this arrow is just a representation of the magnitude of the pressure. So the load area is where the pressure surface and the load area is the contact between the pressure and the object. The plane region is known as the load area. And the surface formed by the plot of the load intensity is called the load surface. So we will not really be dealing with the load surface. However, it is interpreted in there that the load surface is the surface generated by the intensity of the load. And that region V that lies between the load area and the load surface is the magnitude of the pressure. For example, we analyze a differential area on the load area. So it is an infinitesimal area element. Now, the force applied to that differential area caused by the pressure diagram is a differential force, or dr, equals to pressure times differential area. Again, this formula is derived from pressure is equals to force over area. And if you computed for the force, that would definitely be pressure times area. Now, if we analyze a differential area, dA, we can have the differential force acting on dA determined by multiplying the value of pressure on that area and that differential area. The distributed surface load can thus be represented mathematically as an infinite number of forces dr that are parallel to the z-axis. Now, if you try to get the sum of all dr, now you will get the resultant force caused by this pressure on the load area that is parallel to the z-axis. So again, if you add up all the value of dr, you will get the resultant force. So we can say now that the forces, or the summation of forces acting along the z-axis due to the pressure, is the resultant load, which gives us this equation that R is the integral of dr, or if we add up all the differential resultant. So if we substitute the value of dr from the above equation, R now is equals to integral of P times dA. Now we know that the resultant is the sum of the PDA. We would like to know now the coordinate of the resultant. Okay, so imagine this rectangular prism. The volume of this rectangular prism will give you the value of dr. Now, dr now is equals to the height of the prism, that is the magnitude of the pressure, times the differential area, you give dr. Now it says that the total volume of the pressure diagram is the resultant load. Now if you integrate this one, you get the volume of the pressure diagram, and then you will get the resultant. So in short, to get the resultants, that's just simply getting the total volume of the pressure diagram, or using this equation, R is equals to integral of P dA. Now we would like to get the location of the resultant. Since we have the magnitude, it is also important for us to determine the location of the resultant. So as you can see, that the value of moment induced by this dr to x-axis is dr times y. And also the moment induced by this dr to y-axis is dr times x. Now, if we want to take the moments, the sum of the moments given by all of this dr, that is also equal to the moment given by r to the same axis. So if you get the moment of dr about y, and then you sum up all the dr, the moment of all the drs here about y, that is equal to the moment given by the resultant force about y-axis. Now, to get that, or to determine that, we have this equation, that the summation of moment about y of the drs is equals to r times x bar, and we can have the value of x bar. Similarly, when we take moments about x-axis, the moment induced by this dr about x-axis and all other drs is equal to the moment induced by this resultant times y bar. Now the equation above can be reduced since summation of my, or the moment about y, is equals to integral of pxdA. Now if you try to see this pdA, this is the value of dr, and this is the lever arm from the axis where we take the moment. Similarly, we do that here about moment about x-axis. This pdA is the value of dr, and this y now is the perpendicular distance from the x-axis. Okay? And now the resultant could be replaced by equation integral of pdA. And we can also observe that dr is equals to pdA, and that is the differential volume, which I have already discussed. Now replacing the values of integral pdA by integral of dv, since this was previously integral of pdA, we have replaced it with integral of dv because we said that the pdA is equals to the volume of this rectangular prism. Now simplifying the equation from above yields that x bar is equals to integral of x dv over v, and y bar is equals to integral of y dv over v. Now what could we get from that? That means that the magnitude of the resultant force is equal to the volume of the region between the load area and the load surface, and the line of action of the resultant force passes through the center of the volume, bounded by the load area and the load surface. This statement was proven by this equation, that x bar passes at the center of volume of the pressure diagram. So take note of that, because in analyzing or making the free body diagram, it is necessary for us to locate where does the resultant passes, or where is the line of action of the resultant. So again, let's summarize things up. The magnitude of the resultant is equal to the volume of the pressure diagram, and that the resultant of the pressure diagram passes at the center of volume of the pressure diagram. So how about two-dimensional load diagrams or line loads? So line loads are characterized by load intensity W. It is a function of distance measured along the line of distribution. So W is commonly expressed in terms of Newton per meter for SI and pounds per feet in US customary units. So the plot of W is also called load diagram, and here are the common units which I have discussed. And since the unit of load diagram is Newton per meter, that means that for every value of length, there is a corresponding force. Okay? So a straight line load is equivalent to an infinite number of differential forces. So if we consider a differential strip for this load diagram, we have a differential force dr acting over differential length dx. Now the magnitude of that dr is equivalent to the area of that differential strip or that rectangular strip. Now that would be equal to dr equals w dx. And because these forces are parallel, their resultant about z-axis is equals to the summation of forces along z. Or if we sum up all the differential strips here in the load diagram, we get the resultant of this load diagram that is parallel to the z-axis. So we will be using integral or integration to perform or to get the resultant load from the load diagram. Now we have here the value of dr determined from w dx. Now if you get all the dr, or if you sum of all the dr from 0 to a certain value up to the length of the load diagram, that would be integral of dr from 0 to L. And you can replace dr, since dr is the area of the rectangular strip, replace it with w dx. And now we can say the line of action of the total area of the load diagram now is equal to the resultant of the load diagram. So by simple saying, you just have to get the area of that diagram to get the resultant force. But where is the resultant force acting? That is for us to know using this discussion. The line of action of R can be determined by equating the moments about point O. Now, if you take moments about point O by using all the values of dr, or all of this small or all of these differential forces about point O, you would have summation of moment at point O, and those are infinitely number of forces. So the moment of each of the forces is equal to the moment of the resultant. That is why the summation of moment about point O is x dr, and this dr is the differential force for this differential strip, and its lever arm is represented by x. Now, if you integrate all the values of dr from 0 to L and its moment, that is also equals to wx dx. If you replace dr with w dx, you will get wx dx. And that is equal to the summation of moment. Now, simplifying the equation above will give us that the summation of moment at point O is Rx bar. So that means that the resultant passes at the centroid of the load diagram. Okay? So here's the summary. The magnitude of the resultant force is equal to the area of the load diagram, and the line of action of the resultant force passes through the centroid of the area under the load diagram. But as you can see, the load diagram is acting perpendicular to Z in this case only. That means there is no X component for the load, for the force or the resultant force. So it is only important for us to get the value of Y bar, but not the value of Z bar or what. Okay. So for the basic solids and basics area, the centroid for a rectangular solid could be seen by X bar is 1/2 of this dimension B, Y bar is 1/2 of L, and Z bar is 1/2 of H. In this case, for a rectangle, the centroid passes on the half of B and half of H. Okay. How about for triangular surface? The center of volume for this right triangular solid is equals to X bar equals to 1/2 B. For Y bar, that is 2/3 of L. For Z bar, that is 1/3 of H. For a right triangle, the centroid is at 2/3 of B, but if you measure it from this point, that is 1/3 of B. So 2/3 and 1/3. And similarly for H, Y bar is 1/3 of H and 2/3 from that. Okay? So if you are measuring from the base, that is 1/3 from the base and 2/3 from the opposite of the base. So the area of the triangle is 1/2 base times height. So if your line diagram is a triangle, you simply get the area of the triangle, and that would be the resultant of the force. Okay, so to fully appreciate our topic, let's have an optimization problem wherein a line load is imposed on a cantilever beam. But as you can see, this line diagram is not the usual shape we have previously discussed, but we can solve this one by practically dividing this load diagram into region. So our objective is to get the resultant force of this load diagram. So we note that the load diagram is not one of the common shapes that are shown previously. So it is practical for us to divide this into regions in such a way that we can get the area of each region. Okay? So what I do now is I divide the line diagram into three regions, A1, A2, and A3. Now, since previously it is a quadrilateral, it would be tedious for me to get the area and the centroid of this one. However, if you try to uh, make three regions or divide it into three regions in such a manner, it would be easier to determine the area. So what I do now is, again, I have A1, A2, and A3. A1 is a triangle, A2 is also a triangle, and A3 is a rectangle. So let's have first the resultant from the line load in this area 1. Now the value of the resultant from the value of the resultant from area 1 is simply the area of area 1. And that resultant, we will use the term P1 correspondingly for A1, P2 for area 2, and P3 for area 3. Now the resultant force for P1 would be 1/2 times its base 4 and the height of the triangle, that is 15. Now we get P1 equals to 30 kilonewton. So similar step would be performed to area 2, and that would be 1/2 of the base times height. We get 15 kilonewton. And it's easier for area 3 since this is a rectangle. The load for area 3 is 6 times 10, that is 60. Now we have P1, P2, and P3. If you want to get the resultant force of this whole line diagram, you simply need, you will simply just add P1, P2, and P3. Okay? So the resultant now, if you add that up, would be 105 kilonewton. Okay? So since we already get the resultant force, the next question is, where is the line of action of the 105 kilonewton resultant force? Now to do that, let us first determine the location of the line of action of each of P1, P2, and P3. Okay? So from our theory, the moment induced by P1, P2, P3 is equal to the moment induced by the resultant force. So it is necessary for us to get the moment of P1. But before we do that, let's determine the line of action of P1. As from discussion, the resultant force is said to pass on the centroid of the line diagram. Now for P1, this is a triangle. It passes 2/3 from O. 2/3 of 4 from point O. Okay? So x1 is 2/3 of 4 because its base is 4, and we are measuring, if this is the base and this is the opposite of the base, so from this point to this point is 2/3, and from this point to the other is 1/3. That's why x1 bar is 2/3 of 4. And for x2, since this is the base of your triangle and this is the other base, C2 now is measured 1/3 of its base if you measure it from this base. Okay? So this is 1/3. So this is 1/3 from here. 1/3 of the base from here. So 1/3 of 6, this is 1/3 of 6 plus 4. Make sure we have consistent datum, that is 0.0. So x2 would be 4 meters. So why did I use summation of why did I use to measure the values of x bar about y? You can also set different datum. For example, you measure it from this axis. It's all okay as long as you are consistent with the datum. Okay? So how about x3? x3 is in the middle of this rectangle. So that would be 6 divided by 2. So 1/2 of 6 plus 4. So we get 7 meters. Now, since we know the perpendicular distance of each of the resultant forces for A1, A2, and A3 respectively, we can now determine the location of the resultant of these three forces by summing up the moments. So summing up the moments at point O, that would be the resultant force times x bar, and again, that is equal to the moment induced by each of the forces from A1, A2, and A3. So for P1, the lever arm is 2.6. For P2, the lever arm is 6. And for P3, the lever arm is 7. And that would be equal to the value of the resultant times the lever arm of the resultant. The lever arm of the resultant will tell you the line of action of the resultant. And solving for x bar by algebra, we get x bar equals to 5.62 meters. And we could say now that the resultant passes 5.62 meters away from point O. So there we have the diagram wherein we can see the resultant, 105 kilonewton, is 5.62 meters away from point O. So after we have discussed the load diagram, since load diagram are loads imposed on structures or the external loads that will be imposed on structures, and it is important for us to analyze the support of structure before we fully proceed with drawing the free body diagram. Because in drawing the free body diagram, it is important for us to be knowledgeable enough to analyze loads or external loads from the structure and the support of the structure. So the supports of the structures are of different type. The first type we had is a flexible cable of negligible weight. So a flexible cable exerts a pull or tensile force in the direction of the cable with the weight of the cable neglected. The cable forms a straight line. If its direction is known, removal of the cable introduces one unknown in a free body diagram: the magnitude of the force exerted by the cable. So, a support, like the flexible cable, has one unknown. So, if you have a tension here, the reaction of the cable is in this manner or is collinear with the orientation of the cable or the slope of the cable. So this is the reaction of a cable. So the reaction is again collinear with the cable. Tension of unknown magnitude T in the direction of the cable, and the number of unknown is 1. Next type of support is a frictionless surface. So the frictionless surface supports the structure by exerting a normal force that is perpendicular to the contact surface between the structure and the surface that it is leaning. Okay, so since this is a frictionless surface, the effects of friction would not be considered. And again, since it is a frictionless surface, for it to be able to be called the support, it should exert a force that is normal to the surface. So the number of unknown is only 1. Okay. So the next types of support is a roller support. A roller support is equivalent to a frictionless surface. It can only exert a force that is perpendicular to the supporting surface. The magnitude of the force is thus the only unknown introduced in a free body diagram when the support is removed. So here is the roller support. The reaction of a roller support, or the force exerted in the roller support, is perpendicular to the surface. So the force of unknown magnitude n normal to the surface supporting the roller, and the number of unknown is 1. This is similar to the frictionless surface. Next is the surface with friction. This is similar with the frictionless with the analysis of frictionless surface, but there is a factor for the effect of friction. So if this is your structure and it tends to move in this direction, the direction of friction is always opposite to the direction of the movement of object. So you will have two unknowns, this value of F and the normal force on the surface. Because the frictional force also helps in supporting the structure. That's why it is against the movement or the direction of movement of the structure. The next is a pin support. A pin is a cylindrical that is slightly smaller than the hole into which it is inserted. A pin support thus introduces two unknowns. So this is a pin support. A pin support restrains the movement of the structure along two dimensions. So if you have X and Y plane, this hinge or this pin support would restrain the object or the structure to move along X and Y direction. So since it restrained in two directions, there would be two unknowns, Rx and Ry. But this could be resolved into one resultant force. Definitely, there is only one resultant force for this Rx and Ry, and that would be the reaction in the pin support. The reason why it is shown here that there are two unknowns is because it is practical to resolve the reaction into Rx and Ry for the ease of analysis of pin support. And we have the built-in or cantilever support. A built-in support, also known as cantilever support, prevents all motion of the body at the support. So the cantilever support prevents the structure from moving along X, along Y, and it also prevents rotation on this point or at the support point. As you can see, a hinge support allows rotation at this point, whereas a built-in or cantilever support restrains the effects of C. That is why it counters the moment given by the structure, giving you three unknown reactions, which are Rx because it restrains from movement along X, Ry because it restrains movement about Y, and the couple C because it restrains rotation at that point. So you have three unknowns for this type of support. Now, if we have already learned the how we analyze or how we get the area from the how we get the resultant force from the line diagram, and how we get the reactions, it is now ready. We will now be ready in analyzing the free body diagram of the structure. So take note that the free body diagram is a sketch of the body showing all the forces that act on it. That is why it is important for us to learn the line load, because that would be the external forces, and the support because that would be the reaction. The term free implies that all supports have been removed and replaced by the forces or reaction that they exert on a body. So there are two types of forces acting on the body. Those are the reactive forces from the support reaction, which we have discussed. So if the type of support is determined, you already know what are the unknowns. So you can replace those type of support to their equivalent reactive forces. And the applied forces are the load diagrams, the concentrated loads, the couple. This will all compose your free body diagram. So we have discussed these reactive forces, and we have also discussed these applied forces. And those are the forces that consist the free body diagram of the structure. So the first thing we do is to sketch the body that is drawn, assuming that all supports or contact supporting cables have been removed. So the first thing you do is to remove all the support and then draw all the applied forces or the load imposed on the structure. So the weight of the body is considered to be an applied force. Although it is not an external force, it could be considered as applied force. And after you have removed the support conditions, you applied all the forces, the next thing you do is to replace the support reaction, replace the support with corresponding support reaction, and then to finally um, place or to ensure that all dimensions are shown in the figure for ease of analysis. So make sure all the angles are measured, all the dimensions are given. Okay? So to understand how to draw the free body diagram, let's have this problem. The homogeneous bar, 6 meter long, or bar AB in the figure is supported by a vertical plane by rollers at A and B and by a cable at C. The mass of the bar is 50 kilogram. Now our objective is to draw the free body diagram and determine the number of unknowns. So the first thing we do is to remove the support reactions. Okay? So if we remove the rollers at A and B, so the first thing we do is to support. So as you can see, there's no drawing of support. And the next step is to include the applied load. So aside from the weight, there are no other imposed load or external loads shown or given in this situation, only the weight of the bar. Since the bar is 50 kilogram, the weight of this bar is included as or considered as applied load. Now to get the weight of this bar given its mass, simply multiply it with the acceleration due to gravity, that is 9.81, you will get 491 Newton. Now, you apply the value of W at the point of the center of gravity of this bar AB. Why at the center of gravity? As I have discussed, the mass or the resistance passes at the center of gravity. Okay? So after the imposed loads are included in the free body diagram, the next thing you do is to analyze the support reactions. So since you remove the roller at A, the corresponding reactive force for a roller at A is NA, and that is perpendicular to the contact of roller and this surface. Now your direction of NA is upward. Okay, so why is there no NAX and NAY? Because that is for pin or hinge support. But this is a roller support, and we have discussed that for a roller support, there is only one reaction, and that is perpendicular to the surface. Next, we have NB. We conclude that the removal of the roller at support B means that we must show a horizontal force at that point. So, since we remove the roller at B, the corresponding reaction at point B is represented by NB, that is perpendicular to the surface. And since we also remove the support or the cable support at C, we replace it with a reactive force T that is collinear with the cable and is always at tensile direction. Now, a cable cannot support a compressive force but rather always in tension. The reason why it is drawn away from point C and the orientation of the tensile force T is collinear or similar with the inclination of the cable. So after um, drawing all or including all the applied forces and the reactive forces, the next thing you do is to put all the dimensions. So for the dimension of A to C, that is 2 meter, and from the center of gravity to point C, since the center of this 6 meter is at 3 meter, therefore the distance between C and G is 1 meter, and the angle is 40 degrees. Likewise, for this cable, the angle is 20 degrees. And there we have the free body diagram. Now, counting all the unknowns, we have NA, T, and NB. So we have three unknowns and we have three equations of equilibrium. That means this structure is determinate, or we can solve for all the support reactions. Okay, so there are three unknowns. How about in this case, a homogeneous 250 kilogram triangular plate in the figure is supported by a pin at A and a roller at C. Let us draw the free body diagram of the plate and determine the number of unknowns. So the first thing we do is to remove all the support condition. So after we remove all the support, we first introduce the applied load, and the applied load is only the weight of this triangular plate that passes to its centroid. Now, the weight of this 250 kilogram plate should be multiplied by the acceleration due to gravity, which would give us the value of 2,453 Newton. And the location of that W is at G. Now, later we will have this dimension, but on the step that I have shown you, after you placed the applied load, you go to the support reactions. Now, since you remove the support at A, that is a hinge, you replace it with corresponding reaction, which are AX and AY. And for C, the value or the reactive force is perpendicular to this plane, and that would be NC. And after we have included all the support reactions, we now proceed with putting all the dimensions. So the dimension of the distance of W from BA is 0.2 meters, since this is one third of 0.6. So we have 0.2. And the inclination of this NC is 30 degrees by trigonometry. So later we will discuss how we get 30 degrees. So there we go. So why is it 30 degrees? Let's have this basic trigonometry. If you introduce a vertical line, and you have here a triangle, a 30, 60, 90 triangle, and recall that this NC is perpendicular to the surface, and if this is 60, definitely you would have a 30-degree angle. So in short, this angle is also equal to this angle. Now, we know how to draw the free body diagram, and the last of our objective is to analyze the free body diagram by using the conditions of equilibrium. So the conditions of equilibrium says that for a body to be in equilibrium, it should satisfy these three equations. Summation of forces along x equals 0, summation of forces along y equals 0, and summation of moment at any point should be equal to 0. I have discussed this conditions of equilibrium in my previous video, so you might want to watch it for a deeper understanding of these conditions of equilibrium. Now, if you use different axes, for example, you use x prime and y prime, and the x and y directions don't have to be mutually perpendicular as long as they are not parallel. So if you take summation of forces along x prime but not the x-axis, and you have another axis that is not y-axis, which is y prime, you can say that the object is in equilibrium if it satisfies the above equation. Now, you can also say that the body is equilibrium if you have this axis. So summation of moment at point A, and if you have summation of moment at point B, and summation of forces along this axis, you could say that this object is in equilibrium if they are all equal to 0. Now, how about three moment? So you don't want to use summation of forces. If you get summation of moment at point A equals to 0, summation of moment at point B is 0, and summation of moment at point C is 0, Therefore, your object is in equilibrium. In other terms, if you want to analyze the equilibrium of a structure, you may want to get summation of moment at any of the 3 points or any 3 points in the object as long as they are all equal to 0. You could say that the object is in equilibrium. So solving equilibrium equations, the first thing we do is to draw the free body diagram, which we all know we have discussed previously. So it is the analysis is fully dependent on how good are you in making the free body diagram, and make sure that all the forces are properly drawn. Okay? So the second thing to do is to write the equilibrium equation in terms of the forces and couples that appear on the free body diagram. And number 3, solve for the equilibrium equations for the unknowns. Now, let's have the determinacy of structures. Although this topic would be furtherly or deeply discussed in another subject, which is not included in statics of rigid bodies, I would like you to have an overview of what is determinacy. So, a statically determinate structure is in the case that if the number of independent equilibrium equations equals to the number of unknowns that appear on its free body diagram. Statically determinate problems can therefore be solved by equilibrium analysis. So if the number of unknowns for your reactions could be solved by the available 3 equations of equilibrium, your structure is statically determinate. However, if you have too many support and it could not be satisfied by the equilibrium equations, that would be statically indeterminate structure. Okay? So let's have an optimization problem for us to analyze the free body diagram of the structure. So the weight is attached to one end of a rope that passes over a pulley that is free to rotate about pin at A. The weight is held at rest by the force T applied to the other end of the rope, W, that is 50 Newton. So the first thing we do is to draw the free body diagram of the structure. Now we have here, W is directed downward, and the value of T is the support at the cable. And since the support at A is a hinge, if we remove this hinge, we should replace it with corresponding support reaction, which are AX and AY. Now, after we place the applied forces W and T, we next write the support reactions, which are AY and AX. Then after that, let's put all the dimensions. So we have R and the 30 degrees for this cable. Now, on a higher level, let's have the analysis of this free body diagram. Now, taking summation of moments about point A. Can we use summation of forces along X? If we have summation of forces along X, we will have two unknown. The value of the X component of this T or TX and AX. And that is one equation for two unknowns. I don't think this is practical. So let's try to use summation of forces along Y. If we take summation of forces along Y, there will be two unknowns. AY and the Y component of T. Although this W is already given. So we still have two unknowns for one equation. But if we use summation of moment at point A, it could eliminate both AY and AX since they both passes at the moment center A. So I guess this is the practical way to first determine the value of T. Now, taking summation of moments about point A, that would be summation of moment at point A equals to 0. So what are the forces that causes moment about point A? Those are T and its lever arm R, and W and its lever arm R. So we substitute the values. So T is now equals to 50 Newton. Okay, so you will get T minus W equals 0, and replacing W with 50, you get T is equals to 50 Newton. Now, having the value of T, we can now proceed to get the reaction at A. Now, if you get or you use summation of forces along x, there will only be one unknown, which is ax. So summing of forces along x, we have ax plus the x component of this t, that is t sine 30 equals 0, and replacing the known values, 50 Newton for t, we get ax is equals to negative 25. So now the value of this ax, that is negative 25, means that our assumption for the direction of ax is not to the right, but of the reaction ax is instead directed to the left. So we might be wrong in drawing the direction of the reaction. However, we can correct it upon analysis of conditions of equilibrium. Now, you can be wrong with the assumption. If you get a negative answer, that means your assumption for AX is wrong. Because as we have discussed, the support reaction at hinge is R2, AX and AY. But you can assume AY upward or downward, it's up to you. You can also assume AX to the right or to the left, it's up to you again. But if you get a negative value of AX, that means it's the other way around, or the direction of that AX is the opposite of what you have assumed. So in this case, you assumed AX to the right and we get negative 25. Therefore, the value or the direction of AX is the opposite of what we have drawn. So we have to correct that. Okay. So the next step, the only one unknown here is the value of AY. So we will use summation of forces along Y equal to 0. And the forces acting along Y are AY minus the Y component of T minus W. And replacing the known values, we can solve for AY equals to 93.30 Newton. And since we get the positive value, therefore our assumption for the direction of AY is correct. So again, if you want to replace the if you replaced the support with support reactions, make sure you are knowledgeable in how many unknowns you will draw. But the direction could be smartly assumed. However, if you get the wrong direction, you can know the right direction after analyzing the equilibrium. Okay. So let's have another problem. A homogeneous 60 kilogram disc supported by the rope AB rests against a rough vertical wall. Now, using the given free body diagram, determine the force in the rope and the reaction at the wall. So to analyze this structure, let's draw the free body diagram. And the first thing we do is we remove the support reaction. So the first we remove is the tension at the cable or the cable and the friction, the wall that has a friction. Okay, so the next is we put the applied load, that is W equals to 588.6 Newton, determined from the mass 60 kilogram that is given. And the next is we put the support reaction. So for a cable, the support reaction is T and the slope is as shown for 3. And at C, this is a wall with friction. So it has two supports, two reactions, the perpendicular NC and FC. Now this FC is directed upward. It's because the weight of this disc tends this object to move downward, and therefore the direction of friction is against the movement or the possible movement of the object. So we have now the free body diagram of the object, and to analyze that, it is practical to take summation of moments at point B. So summation of moment at point B, it will cancel out NC, T, and W. And the only one that causes moment about point B is FC. So that would be negative FC times 150 equals 0, which we could say that FC is 0. Therefore, the frictional force is not present in the structure. Next, if we have FC equals to 0, we can now have the summation of forces along Y, since we will only have one unknown, and that is the y component of t. So summation of forces along y equals to 0. Those are the y component of t equals to 4 over 5t minus w plus fc. And since fc is 0 and the w is negative is 588.6, we can solve now for the value of t, that is 735.8 Newton. And having the value of t, we can proceed by solving NC using summation of forces along x, and that would be the x component of t, negative 3 over 5t plus NC equals to 0. And then substituting the value of t we have computed, we have NC equals to 441 Newton. Okay? And for the last problem, the homogeneous bar, 120 kilogram, wooden beam is suspended from ropes A and B. A power wrench applies a 500 Newton meter clockwise couple to tighten a bolt at C. Use the given free body diagram to determine the tensions in the rope. So the first thing we do is to draw the free body diagram by removing all the support and replacing it with corresponding support reactions. So drawing the applied loads, we have the weight of the beam, that is 1177.2 Newton, and the couple at C, that is 500 Newton meter. Now to replace the support with support reactions, we have TA for cable A and TB for cable B, and then we proceed by putting all the dimensions. Now, how do we analyze or how can we get the value of TA and TB? It is practical to perform summation of moment. If we use summation of forces along X, we will not get anything. If we use summation of forces along Y, it will give us two unknowns. But if we use summation of moment at a center, that would eliminate one unknown and will give us will yield to only one unknown, that would be practical. Okay, so let's select an equation that will yield to only one unknown, and what that would be summation of moment at A. You can also use summation of moment at B. Okay, what are the forces that causes moment at A? Those are TB, so its lever arm is 4, W, and its lever arm is 3, and the couple, from theory, if you are taking summation of moment, you simply add the value of the couple in the summation of moment. Now, the sign of the couple is based on your assumption. If you are using clockwise positive, if the couple is clockwise, use it as positive. If you are using summation of moment clockwise, counterclockwise positive, if your couple is counterclockwise, treat it as positive. Now in this case, I'm using counterclockwise positive, and the direction of my couple is clockwise. That's why it is negative in sense. So solving the equation above by substituting the known values, we get the value of TB equals to 1007.9. And if we already have TV, we can solve for TA, and by taking summation of forces along y-axis, we get summation of forces along y equals 0. That would be TA plus TB minus W equals to 0. That is TA plus 1007.9 minus 1177.2 equals 0. We get TA equals to 169.3 Newton. So we have now TA and TB. And for the last, we will have a combination of line loads and support reactions. We will analyze a beam consisting of several loads. So to analyze this beam, let us first draw the free body diagram wherein we will remove the support conditions. So these are the imposed loads, the 2 kilonewton concentrated load acting upward, the couple that is 12 kilonewton meter acting counterclockwise, and this load diagram. So for the imposed load, for the support reactions, we have AY for this roller at A, and BX and BY for the hinge at B. And for the resultant of this line diagram, we have 3 kilonewton since the area of that triangle is 1/2 6 times 1, so that's 3. And make sure you indicate the location of that W. So you want to measure it from B, it's okay. But since I measured it from A, we have 10 meters away from A. So W is 10 meters away from A. Now, there are 3 unknowns and we need to choose wisely what equation of equilibrium we will be using for us to get these 3 unknowns. So by taking summation of moment at point A, that makes us eliminate Bx and Ay. And we are left with one unknown in our equation, and it would be By. So taking all the moments at point A, all the forces that causes moment at A are, let's start with the 2 kilonewton force, its lever arm is 3 meter. The 12 kilonewton meter couple, if you add this in the equation, its direction is counterclockwise. That is why it is positive. And W, since it causes clockwise moment at point A, that would be negative 10 W. And for By, since we assume that Bi is acting upward, it causes counterclockwise moment at point A, and that would be positive 12 By. Now, solving this equation by replacing the known value of W will give us By equals to 1 kilonewton. Okay. And for the next steps, let's take summation of forces along X equal to 0, and that would give us this negative Bx equal to 0 because there are no other forces aside from Bx that is acting horizontally. Therefore, negative Bx is 0, and that Bx is 0. So we have now By and Bx, and what's left for us to solve is Ay, and it is also correct to use summation of moment at B, summation of moment at any point to solve for A, but I think it is wiser or faster if we use summation of forces along Y. So summation of forces along Y, the forces acting along Y axis are positive Ay, positive By, minus W plus 2, and replacing all the values of the known. So we have Ay is equal to 0. Now we have Ay, By, and Bx. And that is our lecture for today. And how do we analyze structures involving 2 or more members? Find out in our next video of Static of Rigid Bodies lecture series. Thank you very much.